Okay, now we're up to lecture 7 in the UCL course about how to analyze single channels using matrices. At this stage, we're still at the point where we're trying to specify a model and some rate constants and work out its consequences for observations. That is a necessary preamble to the real question. The real question, of course, being to go the other way round and to take some data and estimate the rate constants in it. And that won't come till the last lecture. All the rest is preamble to the things that we really want to do. Okay, here we go. The question of correlations is an interesting one because it's the only method which will tell you how states are connected. At least in principle it will. And although the algebra looks a little complicated, for example, the joint distribution of the length of an opening and the length of the nth subsequent opening is this rather long-looking thing. I'll show you just how that can be written down almost automatically by using the wonderful notation devised by Alan Hawkes in 1982. So what we're going to talk about is correlation between open times and correlations between shut times and correlations between open and subsequent shut times. It may seem surprising at first that there's any correlation between intervals because it's a Markov process. We presume it's a Markov process. There's no reason to think otherwise. And therefore it's memoryless. It hasn't got a memory. So how can there be a correlation? Well, that's easy to understand, and I'll show you why. For example, open times may be correlated with each other. Long open times, we find for any receptors, are followed on average by long open times, a positive correlation. Open times can also be correlated with shut times. Long openings are followed on average by short shut times in many cases. So there's a negative correlation between them. And as I said, a great advantage of this is that it can give information about how states are connected. And that's something we could get only really from single channel measurements. And it provides another mechanism, another way of testing whether or not a postulated mechanism fits the facts. When we get on to the question of fitting in the last lecture, we'll see that we can get estimates of the rate constants for a specified model mechanism. And we will then want to see whether the fit that we've got is in fact a good one. We'll see whether the fit predicts the open times and shut times accurately. We can also see if it predicts the observed correlations accurately. This lecture is based almost entirely on this 1987 paper, a note on correlations. It turned out to be a rather long note, pages 15 to 52, but that's how it goes. The title was given before it was written. This paper's seared on my mind because in 1984, I recollect very well working on the algebra for it while sitting in a bedroom which the National Hospital had provided for me. adjacent to the intensive care unit in the Maida Vale Hospital, as it then was. And my wife and her baby were at that time, her unborn baby was at that time in the intensive care unit. I didn't know whether they'd live or die, but between going to see how she was, I was working on the algebra. So let's see, first of all, how it is that, despite the Markov property of the independence of sojans in adjacent states, that can be a correlation between open times and shut times. And we'll consider it in the context of this oversimplified mechanism, a receptor binding one agonist, binding two agonists, and it can open when it's doubly liganded. It can also open when it's singly liganded. We can easily see that this can give rise to correlations. The doubly liganded openings are longer than the singly liganded openings. And as we've pointed out, the opening rate for doubly liganded channels is fast, and the dissociation rate is also fast. So the thing that predominates, certainly at high concentrations, will be oscillations between the doubly liganded open and shut state. These openings are long, these shuttings are short, and so there'll be a negative correlation between open times and adjacent shut times. There'll also be a positive correlation between the length of one opening and the next, because the longer openings occur in bursts, little runs. There'll be a positive correlation between the length of one shutting and the next. And most obviously, there'll be a negative correlation between the length of an opening and the length of nearby shuttings, because long openings in the doubly liganded state occur next to short shuttings. Correlations can be displayed and measured in various ways. You can measure them numerically as an autocorrelation coefficient. You can display them as a bivariate distribution, or more informatively as a dependency plot. We'll come to that later. These are both three-dimensional plots. And most helpfully, you can display them as a conditional distribution. For example, distribution of open times for only those openings that are adjacent to short shut times. So what's the definition of a correlation coefficient? For any two quantities, x1 and x2, say, the correlation coefficient is defined in this way. Rho is the symbol usually used for a product moment correlation coefficient. E stands for expectation, and that's just a fancy way of saying the mean value of. So this is, on the denominator, we have the product of the variances. This is a variance for x1, that's the variance for x2. And in the numerator, we have the average value of x1 times x2 minus the product of the means. The means of x1 and x2 separately are mu1 and mu2, and the mean value of x1 and x2, x1 times x2 can be found from the joint distribution. That's all detailed in the paper in much more detail than we do it here. Let's just have a look before doing that at what these various ways of displaying a correlation. I'm not going to do it for the exponential distribution because that's harder to see, I think, in many ways. Let's just do it for a Gaussian distribution. This is a bivariate distribution for x and y, where the distributions are all Gaussian. Plotted as if we plot that as a contour plot, just looking down on it, so we have x and y on the axes and the height coming out from the screen, it would look like that. And what that means is that if you take slices across here at a constant value of y and look at the value of x, we're starting at y equals -2 and going up to x equals +2, and we see it looks like that. Because this is symmetrical, the mean of the x value doesn't depend on which y value you take it as. That's what independence means, or sort of uncorrelated means anyway. If we now go on to a case where the x and y are positively correlated, then the 3D plot of the joint bivariate Gaussian distribution would look like that, or in contours it would look like that. The contours are tipped relative to the axes, and what that means is, if we imagine sections of this taken at a fixed y value, then the mean of the x's is going to be smaller when y is smaller and bigger when y is bigger. So the sections going from y equals -2 up to y equals +2 would look like that. And you can see that the mean value of x depends on what value you take y at. That's what a positive correlation means. Okay, so now we'll do a couple of reminders. This was all dealt with in the matrix lecture, lecture 2, but that was some time ago now, and we'll go through it again just to remind you because it's rather important. We often use lowercase letters for vectors, in other words, matrices with only one row or one column. You have to know or work out from the context whether they're rows or columns usually. We'd written our initial vector, the phi, as a row vector, and here we have a unit column vector. By unit, you mean that all its elements are 1. And it's important to realize that a row times a column gives you a scalar number. That's a row, you use a column. So writing them out, if they're 1 by 2 or 2 by 1, is that, and you see that the product is simply the sum of the elements of the row vector. So it's a scalar number. That's 1 by k, k by 1. So the result is 1 by 1. On the other hand, a column times a row gives you a matrix. If we reverse the order of these, just for this example, the column vector u times the row vector phi gives this, and that gives you a matrix which the columns of which are the elements of phi. That's k by 1, that's 1 by k, and this is k by k. There's also a quite different notation used for vectors, mostly by physicists, but I won't go into that now because it's not used in the stochastic literature. Okay, now here's a second reminder slide, the wonderful G matrices. In this case, we want the GAF matrix where A is the set of all open states and F is the set of all shut states. And that we have shown is given by the exponential of QAAT, which is in fact the Ka by K matrix itself times QAF. That's the sub matrix of the Q matrix. The elements of GAF of T, we call them the elements in the ith row and the jth column, Gij of T, and these elements give the probability densities for staying within the open states, that's set A, for a time t, and then leaving for shut state J, conditional on starting in open state I. This is the standard thing that was first written down in the 1982 paper. And the Laplace transform of that we have seen is given just by this. It's directly analogous to what it would be for a scalar exponential. And continuing that reminder slide, we should also recall that if we want the probabilities of transitions from open states to shut states, regardless of how long those transitions take, we find that by integrating GAF over time, and we can do that most conveniently simply by setting S equals 0 in its Laplace transform. So this Laplace transform, G star AF of S, we set S equals 0, and we get simply this. And we denoted GAF to get rid of all these excessive encumbrances in the notation. So this gives the probability of these probabilities regardless of how long they take, and we simply omit the time argument, GAF of T. We just write GAF without the T. That means we've integrated over time. In this case, because an open channel must eventually reach one or other of the shut states, the row sums of GAF must come to 1. The row sums of GAF times the unit column vector, and that must equal a unit column vector. And very similarly, GFA UA must equal UA, and GAF GFA, that's the probabilities of we're going from open states to shut states and back to open states. We must eventually reach one or other of the open states, so the row sums of that must also be 1. The other thing we need to do to define autocorrelations is to define the lag. We'll do it only in terms of open times now, but the very similar definition holds if you're considering the correlation of open times and shut times, or shut times with shut times. So the correlation coefficient between the length of an opening and the length of the next opening has lag equals 1. That's the correlation between these two numbers. The correlation between the length of an opening the length of the next but one opening has lag equals 2. The correlation between the length of an opening and the length of the next but 2 has lag equals 3, and so on. The length correlation between the length of this and the length of that has n equals 4. Okay, so now the algebra starts. What we need to get the correlation coefficient is the joint or the bivariate distribution for the length of an opening T0 and the length of the nth subsequent opening, Tn, say. And the wonderful thing about the Hawkes notation is you can write this down almost straight away. We start off with our usual initial vector for openings, and this represents the time spent within shut states of T0, that's the first opening. After that, we have n-1 transitions from shut to open and open to shut. And then we have, and the time spent in those is irrelevant for the autocorrelation coefficient. And then we have the nth opening, which is described by this term. So that's the joint distribution. It looks long, but it makes perfect sense. With a bit of manipulation, you can get it into this form. Be good practice at these things if you try that for yourself. So the average value of the product of the two open times can be found from this. The exponentials are replaced by that essentially, just as they were when finding the average of a simple open time. For the individual openings, as we've seen in the last lecture, the distributions look like that, and the separate means look like that. So if you put all those together into the definition of the correlation coefficient, we get the correlation coefficient between the length of an opening and the length of the nth subsequent opening is given by this. The product of the variances is at the bottom, and the top bit comes from the bivariate distribution. It's perhaps not immediately obvious that this is what you get, but if you, I'll leave it to you to plug in the previous relationships and see that they come out to that. Of course, what we want to do is to express it in an all-scalar form in the end, and to do that, we use, as usual, the wonderful spectral expansion trick, Sylvester's theorem. In this case, what we want to, the spectral expansion of, is this term, GAF times GFA. That's a Ka by Ka matrix, of course, so we can abbreviate it as XAA. And because, as we've seen, this matrix has rows that sums to 1, it's always going to have one eigenvalue which is equal to 1. So we can say that's the first eigenvalue if we want, and the spectral expansion matrix, the spectral expansion of this looks like that. A1 times the first eigenvalue, which is the unit eigenvalue, A2 times the nth power of the second eigenvalue, A3 times the nth power of the third eigenvalue. And the wonderful trick is that it turns out that A1 is of course a Ka by K matrix, and it's just the unit vector times phi 0. So that's the initial vector for openings. So it's a k by ka matrix with rows that are all equal to phi 0. And because all the other eigenvectors of this matrix are less than 1, these terms gradually disappear as n increases. And that means that as n increases, all the terms vanish except the first one, and the first one tends towards A1, which is UA phi 0, phi O, sorry, the opening vector for openings, the initial vector for openings. And so that term tends to this term, and that means that these cancel out and that the correlation decreases to 0 as n increases. That makes perfect sense, of course, because the correlation you expect to be maximum for events that are close to one another. And as they get more distant, you'd expect the correlation between them to decrease. So far, and in fact in the rest of the lecture, all we've talked about is the correlation between open times and subsequent open times. In fact, they're usually rather weak in the records that we've seen, and the correlations between open times and shut times are stronger. But the wonderful thing about the Hawkes notation is we can find the correlation between shut times and subsequent shut times, or the correlation between open times and subsequent shut times, simply by changing the subscripts. What turns out to be important for correlations is the rank of the matrix. Again, this was dealt with briefly in the second lecture about introduction to matrix algebra, and I'll go into it a little bit more now because it turns out to be important. For any matrix with KR rows and KC columns, the rank of the matrix is defined as the number of linearly independent rows or columns that it contains. That's not easy to spot. An easier definition is the maximum value of R for which there remains after deleting rows and columns a non-singular R by R submatrix. That's much easier to determine. I hope this will be clarified by the examples we give in a minute, but here are some rules which apply for ranks. It can't be bigger than the smaller of KR and KC. A 2 by 3 matrix can't have a rank bigger than 2, for example. A square matrix has full rank if it is not singular. A square matrix K by K is singular if it has one or more 0 eigenvalues, because that means that the determinant is 0. That's what definition of a singular matrix is, one whose determinant is 0, and because its determinant is a product of all the eigenvalues, then one or more 0 eigenvalues means that a matrix is singular. There's a number called the nullity, which is the number of 0 eigenvalues that a matrix has. That's easy to determine numerically. with the computer program. And for a square matrix, the rank usually has the full rank k minus the number of zero eigenvalues. And in a square matrix, the presence of a row or column of zeros will reduce the rank by 1. That's easy to determine. The Q matrix, for example, is k by k. We've seen that it usually has 1 zero eigenvalue, so its rank is k minus 1. We've also seen that the QAA submatrix, the bit that refers only to transitions between open states, is usually not singular, so its rank is Ka in almost all cases. And lastly, if you multiply two matrices, the rank of their product can't be bigger than the smaller of the ranks of the two matrices separately. So we can see how to go ahead now with the correlation coefficient between two open times. With the help of the spectral expansion, the correlation coefficient as a function of the lag can be written in this way as an entirely scalar thing. It's the matrix, it depends on the eigenvalues of GAF, GFA, and the weights can be calculated from the eigenvectors, just as areas of distributions can be calculated from eigenvectors. In this case, the weights turn out to be that the weight for the mth eigenvalue depends on the mth A matrix, and everything else can be calculated from the Q matrix in the usual way. So how many components will there be in this decay of the correlation towards zero? Well, at most, the number of open states minus 1. But it'll be smaller than Ka minus 1 if any of the eigenvalues of GAF, GFA are 0. In fact, it turns out that in general, the number of components will be the rank of this matrix, which was central to our calculation of the correlation coefficient. The rank of that minus 1 is the number of components you expect. And in general, this is where the connection comes with the way states are joined up. The rank of the number of open and shut states that have to be deleted to completely separate the open and shut states. That's called the open-shut connectivity, and it turns out to be the rank of the matrix. Here are two examples. This is the two bindings to shut states and opening of the monoligended and opening of the diligended receptor. And this is exactly the same, except that there's no connection between the monoligended shut receptor and the monoligended open receptor. That's not likely, perhaps, but it'll serve to illustrate our example in the simplest possible way. In this case, you have to delete two states, these two states, 3 and 4, in order to completely separate open states from shut states. But in this case, you only have to delete one state to separate open and shut states, either 2 or 3. So the connectivity is 2 in this case, and that shows that there will be correlations probably, although decay with a lag as a simple geometric distribution, one component. But in this case, the connectivity is 1, so there'll be no correlations at all. The connectivity is 2, we'll see, is the same as saying that the rank of GAF, GFA is 2, and saying that the connectivity is 1 is saying that the rank of that matrix is 1. So the GAF matrix is, we had seen repeatedly, is defined by that. QAA is non-singular, so it has a full rank KA. So the rank of GAF will usually be the same as the rank of QAF, because that's full rank, but this is less than full rank. Their product will be less than full rank. Here's the model, the Q matrix for the model we were dealing with. This is the case where you could open from either monoliganded or biliganded states. We partition it into open states, QAA, transition between shut states, QFF, and QFA here, QAF there. We see that QFA is given by that. QAF is given by that. These are open states to shut states, so they contain the shutting rate constants. In this case, the rank of QFA and of QAF, and therefore of GAF, GFA, are equal to 2. In this case, though, the case where the monoliganded receptors couldn't open directly, the rank would be 1, because this now has 2 rows that are 0, and that has 2 columns that are 0. That reduces the rank to 1. In that case, the eigenvalues of GAF, GFA, there are 2 open states, so there are 2 eigenvalues. One of them is 1, as always. The other is 0.2. But in this case, the eigenvalues of that are 0 and 1. Likewise, the eigenvalues of GFA by GAF, that's KF by KF matrix, 3 by 3 in this case, and it has eigenvalues which are 0, 0.2, and 1. So in this case, we see no correlation. In this case, we see a correlation with one component, and it is the decay of the correlation coefficient with increasing lag is given by that. each extra lag, the correlation coefficient is 21% of what it was for the previous lag, so it decays rather rapidly. I pointed out that the dependency plot was a way which was introduced by Magleby and Song. I'll put that a link in the description for that, as a nice way, a better way to show correlations than plotting the bivariate distribution. It makes things more obvious. This is for an open time and for an adjacent shut time, say. So the bivariate distribution divided by the product of the separate distributions for open and shut times, and that's -1. And it's defined in that way because it'll be 0 if the open times and shut times are independent, because in that case, the joint distribution is just the product of the separate unitary distributions. So if you look at the joint distribution of open times and shut times, it looks like this. It's not easy to see correlations in that plot. But if you look at the dependency plot, it's much easier. The bits that are 0 here are no dependency, but long shut times, long shut times up here tend to occur next to short open times. And they're positively correlated, but negatively correlated where the plane sinks below 0 are short open times and short shut times. Even that's not that easy to look at, I think. And a better way to do it still, I think, is to use conditional distributions. Three-dimensional distributions look pretty, but they aren't easy to read stuff off. Now we want to, I think the simplest way of showing correlations is to use a conditional distribution, because it can be plotted in 2 dimensions. Three-dimensional plots look rather beautiful, but they're really not very good for, not very useful in practice, except in a qualitative sort of way, because it's very hard to read anything off them. So here are some conditional distributions. The blue histogram there shows the distribution of, not of all open times, but only of those open times that are adjacent to short shut times less than 100 microseconds. The red dashed line shows the distribution of all open times, not the ones that are, not only the ones that are less than 100 microseconds, but all the shut times. And we can see that in this conditional distribution, there are far fewer short openings which are adjacent to short shut times than there are in the unconditional distribution. Likewise, there's an excess of long open times adjacent to short shut times compared with the distribution of all open times. And conversely, if you look only at the open times which are adjacent to long apparent shut times, 1 to 10 seconds, say, you find the opposite phenomenon. There are once again, the red distribution is the distribution of all open times, but if you look at only at the open times that are next to long shuttings, then they are longer than average. And if you look only at the open times which are next to long shuttings, then you have fewer than expected long openings next to long shut times. We'll come back to those when we do the fitting, because these involve fits, and therefore they involve compensation for the fact that you can't see short shuttings very often. Okay, the last slide in this will show an interesting phenomenon. This is from a paper that I did with Alistair Gibb. It's actually an NMDA receptor, unusually. And there's no fit of a mechanism involved in this, they're just observations. If we look, this is a more synoptic view again than the conditional distribution. We look at the mean of the open times which are adjacent to shut times in a specified range, then next to short shut times, you see on average the open times are longer. Next to long shut times, we see on average that the open times are shorter. Once again, there's a negative correlation, just as in every sort of receptor we've looked at. But how can the mean open times change in that way? Because their time constants are the time constants of the QAA matrix. They don't change with time. So it's not, and in this we showed, I hadn't seen this before, but it was rather nice, that the time constants don't change just as you'd expect from a Markov process. The time constants, there are 3 time constants fitted to the empirical distributions. They should come from the eigenvalues of minus QAA. And in fact, they were the same in all of these distributions. What changed was the areas of the distributions. The open times decrease when they're next to long shut times, because the fast component of the distribution gets bigger and the slow component of the distribution gets slower. And that's where the dependency of this arises. And the fact that these don't change with the adjacent shut time is good evidence that the Markov process is a good description of the results. So next time we get on to single ion channels following a jump in concentration or in voltage. So far, all we've dealt with is equilibrium processes. Synapses don't work at equilibrium, so it is very useful to be able to think in terms of single ion channels after a jump.